Hi, team. I want to give you more exponential relationship examples, okay? So thank you for showing up for your learning today about exponential relationships. And we're going to go over a few examples. Now, things that are related exponentially, they grow or shrink by multiplication or division, not addition or subtraction. So many things in our world work this way. They grow by multiplication, they grow by division. Think about animals. Okay, they multiply. We don't say they add. We don't say that population of rabbits is adding very quickly. We say that population of rabbits is multiplying very quickly. That's because we use multiplication to chart its growth. All right, now money works this way too. Viruses work this way, so do viral videos. Okay, countless things in our world work through exponential relationships. So you're going to develop your ability to understand the universe better by understanding this mathematics better. Okay, so a viral video will be our first example. Okay, and I want to just turn on the lights in the room because they go off when I sit still preparing you things for a while. Okay, so this viral video, every day the number of people who see this viral video quintuples. Quintuple is a word that means grows by a factor of 5. It means we have to multiply by 5 to quintuple something. To double something, you multiply by 2. To triple something, you multiply by 3. To quadruple, it's by 4. Quintuple is by 5. And then, really, I wouldn't say like sextuple. It sounds weird. Or septuple or octuple. These are odd words, but quintuple is a word that you will hear. Okay, it grows by a factor of 5. So, 8 people have seen the video today. How many will see the video after 3, 10, and 100 days? One strategy to understand this relationship is to draw a table. Okay, here is the day. Okay, and we want to start these at day 0. Today is day 0, it's 8. Okay, and here is number of people. That was given. On day 1, it's going to quintuple. So I will have 8 times 5 equals 40 on the next day. On day 2, that's going to quintuple as well. So I will have 8 times 5 times 5 equals 40 times 5. So I wrote it that way for reasons. Okay, 40 times 5 is 200. Okay, and on day 3, I'm tired of drawing all those 5s. It's 8 times 5 to the 3 equals, well, 200 times 5, 1,000 people. 1,000 people will have seen it. Okay, how about on day 4? And maybe I'll notice a pattern. 8 times 5 to the 4. Oh, look at that. I got a pattern. See? 8 times 5, 8 times 5 times 5, 8 times 5 times 5 times 5, 8 times 5 times 5 times 5 times 5. Okay? So it's just the number of times I've multiplied by 5 is given by that exponent. Aren't exponents really useful? Oh my goodness, it's so great. Okay, and what is that? Well, it's 5,000. All right, so this is what your calculator would tell you these things are. And what days did I ask? 3, 10, and 100 days. Well, I've already seen the pattern. So now I can just go in here to my chart, and 10 will be 8 times 5 to the 10. Okay, and 100 days will be 8 times 5 to the 100. Let's see what these are. Okay, so what's 5 to the 10? We use a calculator for that. Or you can use a piece of paper and do lots of multiplication. That's good practice. Okay, 5 to the 10 equals, okay, so that's a big number, 9,700,000. So we're already maybe using scientific notation to write that number down. We're going to multiply that by 8. It's going to have a lot of zeros. Watch this. It's going to have 3 zeros. Equals. Amazing. How did I know that? If you know how I knew that, tell me, and I will know that you know that too. So 78 million people. So I'm going to write that down in scientific notation. 7.8 times 10 to the 6, 7, 10 to the 7. Note that's not an exact answer, but I don't care. I've rounded off a statistically insignificant part. The 125,000 people that I'm ignoring here by rounding are insignificant compared to the 78 million that I've included, okay? Now, let's clear that. We'll do 5. We'll see how many people after 100 days Do you think it's going to be the population of the world or way more than the population of the world? It's going to be way more. Oh my goodness. It says, what does that mean? And then I have to multiply by 8. Okay, so this is 6.3 times 10 to the 70. Oh, wait, yeah, 70, yeah. The e plus 70, that means multiply by 10 to that exponent. This is my calculator giving me scientific notation back. So that's a 6 and then 70 zeros after it, okay? Okay, viral videos don't grow this fast, or at least they don't continue. They can grow that fast for a little while, but then they plateau. Same with viruses too, fortunately. Okay, so that's pretty amazing. All right, so that's pretty crazy. So let's write our therefore statements. Therefore, after 3 days, 1,000 people have seen it. After 10 days, think of that, 1,000 people after 3 days. After 10 days, 10 days we had 78 million people. And the human population is only about 8 billion. Okay, so here we're at 6.3 times 10 with 70 zeros, way, way, way more than the entire human population. And we get a nonsense answer of 6.3 times 10 to the 70 people after 100 days. That's really important to be able to know that that's nonsense. Okay, sometimes your calculator will tell you things that's nonsense, and you need to be able to recognize that. Sometimes it means you've made a mistake. I haven't made a mistake here, just the mathematical system we're using to say how many people will have seen that video is nonsense after a certain point. Okay. This one, no. This one is pretty good. A car depreciates or loses value. Okay, this is what happens when you buy a car. It will start to lose value and eventually be worth very, very little. Okay, but when it's new, it's worth a fair bit of money. Now, this car loses value such that every 4 years, its value is halved. It loses half its value every 4 years. Okay, so if it's worth $64,000 today, how much will it be worth in 4, 8, 12, and 40 years? Okay, so again, we can use a table strategy to start, and then we'll discover an equation that can help us do the bigger numbers. We don't have to do the table to 40 entries. Okay, so here we have year and we have value. Okay, I'll do these in a different color just so you see them a little more clearly. So in year 0, that's now, it's worth 64K. K means 1,000. I could have also said 64 times 10 to the 3, but we say 64K to mean 64,000. All right, in year 1, I'm going to take 64,000, okay, that's 64K, and I'm going to multiply that by 1/2. It's the same thing as dividing by 2. And that equals 32,000. Wow, Mr. Jennings, you sure gave us a nice number to work with initially. I did. I very much did. Okay, so now let's see what happens when we go to year 2. Okay, year 2, we're going to have 64,000. Wait, maybe that's confusing some people. What I'm going to have in year 2, let's really take a look at this, is I'm going to have 32,000, and I'm going to have it again. But now here's an equation, and that's going to be equal to 16,000. Okay? You can do these on a calculator and find that that's true. Okay, but let's talk about this for a second. Where did that 32,000 come from? It came from here. It's another way of writing that. Here's another way of writing that. So let's just bring this up here, and we'll expand it a little bit. If we write 32,000 in a new way, we could write that as 64,000 times 1/2. That's 32,000 there. And then I multiplied that by a half to get this. So I'm going to multiply by another half equals 16,000. Oh, I could write that in another way. It's 64,000 times 1/2 squared. Oh, there's the exponent. It shows, I multiplied by that twice. Okay, so that's how we can use exponents in these cases. That's one way to do it. Another way to do it would be to use a negative exponent. If you can do it that way, cool. You understand negative exponents really well. I would do it that way, but you don't have to. Okay, so now we wanted to know, oh, I did this wrong. Oh my goodness, and I'm not going to re-record the video. I'm going to preserve my mistake as a demonstration of growth mindset. I forgot that it halves every 4 years. So this is not year 1, this is year 4. And then this is not year 2, this is year 8. Okay, this is the first time it halves its value. This is the second time it halves its value. And then we want to look at 12. Okay, 12 years, it will be another 4 years, it will halve its value again. So we will have $64,000, the initial cost, times 1/2 to the 3 equals, okay, well, it'll be half of that, 8,000. All right, now let's keep having it until 40. Let's figure out how many times did it have its value. Well, if it halves its value every 4 years, it must have halved its value 10 times. So I'm just going to put a little bracket here, 10x, okay, just to remind myself. I'm going to continue drawing my chart, and I'm going to bring this over. 64,000, what's up with that little mark, Mr. Jennings, times 1/2 to the power 10 equals, I'm not really sure. 2 to the power 10 is a bigger number than 64, so let's do it on a calculator. Here's how you do it on a calculator. You could say 64,000 multiplied by 0.5. 0.5 is the same thing as a half, right? Maybe you don't like that. Maybe you want me to write bracket 1 divided by 2. Okay. And see, it tells me 1/2, okay, is 0.5, raised to the power 10 equals $62.5. $62.5. I'm feeling a little weird about that. If it halves 10 times? What? That can't be right. Equals. I am very confused. I think my calculator is fooling me. I'm not usually using this calculator. So let's check it. So you see when you get a fairly nonsense answer, you want to check it. So let's do it. 64,000 times 0.5. This is 4 years, 8 years, 12 years, 16 years, 20 years, 24 years, 28 years. Oh, it is right. Wow. 32 years, 36 years, and 40 years. Okay, so it was correct. 62.5. It's only going to be worth a little less than $100 after 40 years. Actually, now that I zoom out a little bit, after 40 years, what's the car going to be worth? Yeah, very little money. Now, it might plateau earlier than that. It might have a certain value as scrap metal that it never goes underneath. And so those are some of the strange things. This is already kind of a nonsense answer that a car could be worth only $60, but because you can always get like a couple $100 for the scrap metal. That's why this was confusing me. But this is such a big number. 40 years into the future, what's it going to be worth? So there we go. Therefore, the car will be worth only $62.50 in 40 years. Cool. Okay, so that's a little bit more challenging example. But the only really thing that's weird there is we have a fraction that is the base of an exponent. But we want to be comfortable with that. We want to know that we can just do that. And you can just do it on your calculator for now. Next unit is more about fractions, so we'll be spending more time with that idea. Last example, and this is a more challenging example. It's an example that's above the level of a grade 9 class, but I want to make a connection to a video game that I used to play when I was about your age. And there was a spell in this game called Static Field. And Static Field was unique because it did not do a set hit point number of damage. It didn't do like 100 damage. It did damage as a percent. It did 25% damage to whatever you were hitting. So if you're hitting a monster with 10 hit points, it did 2.5 damage. It did like hardly anything. But if you hit an enemy with 100,000 hit points, then it would do a great number of hit points of damage. So it was a very powerful thing to use correctly. Let's see some of the ways that you could use this. Okay, so let's say we know that it's reducing hit points by 25% for every casting. So let's see what happens. 25%, another way of thinking about that is it's 1/4. It's 1/4 of their hit points. So if I have their whole hit points, which is 1.0, and I subtract a quarter, which is 0.25, how much am I left with? Well, that would be 0.75 of their hit points. Or in other words, or 3/4 is what they will have left. Okay, so this is how much the hit points the monsters are left with after one casting. So let's see, we have this enemy with 10,000 hit points. Okay, so let's say we have number of castings. How many times have they been hit by this spell? Okay, and then we'll have hit points. If we've cast a spell 0 times, they will have 10,000 hit points left. They'll have their full hit points. Okay. If we cast it once, well, they'll have 7,500 hit points after one casting, right? But how do we get that? Well, that was equal to 10,000, their original hit points, multiplied by 3/4 to the power 1. That's where my power is going to go. And it's going to go on this more complex fraction that has a numerator and a denominator. Okay. It's just a little bit more complex, but the math is exactly the same as the other examples that we've looked at. So we want to know 1, 2, and 10 castings. So here is 2 castings would be this times 0.75, or this times 3/4. 3/4 is equal to 0.75. Okay. They're the same thing. Just this is decimal form, this is rational form, fraction form. So if I multiply 75 over that, well, it would be, what I can do is I can say, if I want to do this in my head, I can't do this decimals in my head. I'm not very good at that. Multiplying this by itself, yuck. But what I can do is do 10,000 multiplied by 3/4 squared, which is equal to 10,000 multiplied by 3 squared over 4 squared. Okay, this square squares the top and the bottom. So it's 9/16. 9/16. This, if I do that, I can also do that multiplication in my head, but you don't want to watch me. Okay, if I do 9 divided by 16 equals multiply 10,000, then it's going to be 5,600 damage. 5,650. Okay, so that's how much is left after 2 castings. All right. 25, not 50. 25, and that's a mistake. Okay, so that's how many hit points are left after 2 castings. Notice that it's a little more than half of their initial hit points. But you'd think, well, I took away a quarter once, and I took away a quarter another time. Shouldn't they be at exactly half? No, because you're decreasing the current by a quarter each time. Okay, so this takes off exactly a quarter. This takes off a quarter of 3/4. It doesn't take off the initial quarter. The amount of damage done with each casting decreases every time we cast it because it's growing by multiplication or division. Okay, now if I want to know 10 castings, here I'm going to use an exponent. And I've already kind of run out of space, so let's go up here. If I have, here's the initial hit points, 10,000, and then I'm going to multiply that by 3/4 raised to the power of number of castings, 10. And so then that would be, well, what is it? Here is how you do it on your calculator. 3 divided by 4 gives me 0.75. I raise that to the power 10, and that gives me, it's about 5.6%. So they'll have 5.6% of their initial hit points left after 10 castings. Okay, and so then I multiply that by 10,000. And that gives me the answer. They'll have 563 hit points left. So with 10 castings of this spell, we've done nearly 10,000 points of damage, about 9,400 points of damage in 10 castings. And so that's working out to an average of about 900 points of damage per casting. But if we kept casting, would they ever die? Would they ever die? And the answer might not surprise you now. Okay, if I have, and here's why, 3/4, and we're going to raise this to a power x. Okay, I don't know how many castings I'm going to do, but I'm going to do some number. All right, we can graph that. Okay, let's graph it in our graphing calculator, Desmos. So here we go, Desmos, and here we go, graphing that relationship. So I'm going to put in here 10,000. I'm going to multiply that by 3/4. And I'm going to put the bracket in the right place, Mr. Jennings, and I'm going to raise that to the power x. I said raise it to the power x. There we go. And now we can't see anything. Well, it's because we need to change the scale. So over here, let's just go ahead and we're going to look at, we'll look at 100 castings of this spell. Okay, and we will look at, we want to see the initial value here. There is 10,000 hit points. So here is the monster's hit points after, and this is what happens as we continue to successfully cast this spell. It looks like it's just plummeting, going down really fast. But then the spell stops being as efficient. They say around 10 castings here that we looked at before, and there's that number that we had about 563 hit points, 564, 563 hit points at 10 castings, and then so on and so on and so on. At 20 castings, it only has 31 hit points left, which is pretty cool. I'll make this bigger so you can see it a little better. Okay. So here is, at 20 castings, it only has 30 hit points left. But at 40 castings, it still has like some non-zero number of hit points, 0.098. After 60 castings, it says 0, but if I really zoom in there, okay, if I zoom in, you'll find that this is non-zero. Yeah, it's showing it as 0, isn't it? It's basically 0, but it's not. If I really zoom in. So I want to show in my x-axis just that, and in my y-axis, I don't nearly need as much. I just want like 1. And I don't need any negatives. So there we go. Here's 1, here's this, and see now it's showing me the decimal. Okay, it's still above 0, and it's just growing smaller. And so it's doing something called approaching 0, but never touching 0. So this spell could never kill an enemy. It could never get a kill shot because it would always take away some percentage of their remaining health, which would always leave them something. So you need someone there with a big sword to hit them and do some subtraction damage to bring them below 0. And that would be how you would finish off your enemies. So that's just another example of exponential growth and decay, and some of the interesting examples that you might find around you. You'll explore these types of functions a lot more in grade 11 and get to look at especially the financial applications of them. A hint, interest rates are growing your money through multiplication. And also loans and interest that you pay on credit cards and things are taking money away from you with multiplication. So you want to be on the right side of that, and understanding it's going to help you do that. So thank you very much for showing up for your learning. I hope that your math practice is productive today, and I wish you all the best. Bye. Bye for now.